So, good evening, everybody. So, let's start today's topic. So, what we are going to discuss? We are going to discuss the time evolution of any physical quantity in some system, obviously. So, in last class, we have seen what is Poisson bracket, and before that, we have seen what is Hamiltonian. And now, we will just club these two things, and we will see how we can have time evolution of any physical quantity. So let's try to understand, and then we will see that what is meaning of conservation, and how any physical quantity can be conserved in some system. If I am talking about some system, means I am talking about, we know the Hamiltonian of this particular system, and then we will see which kind of analysis we can do from this particular chapter. So let's go for, suppose we have Hamiltonian of a system, and this Hamiltonian is basically function of generalized coordinate, generalized momentum, and obviously time. And what we want, we have one particular function, and this function can be any physical quantity. This can be also defined in a generalized coordinate, generalized momentum, and obviously time. So this is my function f, and this is my h. What we want to know that this particular function, how this particular function evolve for this particular Hamiltonian. Means, suppose you want to say that linear momentum is conserved in free particle, means we know the Hamiltonian of free particle. Similarly, we can analyze the linear momentum is conserved in harmonic oscillator or not, means we know the Hamiltonian of harmonic oscillator. So let's try to go for this. What is this particular thing? What we have? We have df upon dt. So this is the time evolution. Whenever we are talking about time evolution, we are just talking about the total derivative f with respect to t. So this is del f upon del qi dqi upon dt. Obviously, we have to go for summation over I, plus del f upon del pi dpi upon dt, and obviously these all are in the same bracket, and we have del f upon del t. Dt upon dt is 1. There is not any problem. And we know the Hamiltonian for this particular, so we know the Hamiltonian of system, means we know the Hamiltonian equation of motion. What we have del h upon del qi is equal to minus pi dot, and same time we can just go for del h upon del pi is equal to qi dot. So what we can do, we can replace qi dot, this is nothing but qi dot, this is nothing but pi dot. We can replace qi dot with del h upon del p, and similarly we can replace pi dot minus del h upon del qi. So what we have? We have df upon dt, and this will be del f upon del qi, and this will be nothing del h upon del pi plus del f upon del pi, and this will be minus del h upon del qi plus del f upon del t. What we have? We have wonderful equation del f upon del qi del h upon del pi minus del f upon del pi del h upon del qi plus we have del f upon del t. What we have? We have this particular term is just identified as Poisson bracket between f and h. So this term can be written as Poisson bracket between f and h. What will happen? We have df upon dt is equal to f h plus del f upon del t. So this is the thing. Now, this thing will be constant. F will be constant only when. So this is, so we have df upon dt is equal to 0. Then only f is constant, which means I can say f and h, the commutation of f and say must be equal to minus del f upon del t. If these only hold, then only f will identified as constant of motion. Just you can have this particular frame. If you have any doubt, you can just ask me. Then we will go for next level.
Sir, what does this signify?
What does significance we will see later. First, you can just see the calculation. We will just discuss it. We will just discuss it.
So I'm not getting the part that Poisson bracket of f and h is equal to minus del f by del t. The last thing you explained.
What is problem in this? Just tell me. If I want del f upon del t is equal to 0, then this must be hold. What is problem in this? Isn't it? When df upon dt will 0.
Okay. Got it. Thank you.
So this is simple. df upon dt will 0 when this will equal to this. That's it. Now, your question is very genuine. I am just coming on to that part. First, you must appreciate all this thing. You must appreciate all this thing. So now, what we have a very interesting information. If we know the some function, and with that function in term of generalized coordinate, generalized momentum and time, look at here. It's a very important thing. What we have df upon dt is equal to f and h plus del f upon del t. This f will constant of motion. It may or may not be constant of motion. When it will constant of motion, f will act as a constant of motion. Constant of motion when f df upon dt is equal to 0. And when df upon dt is equal to 0, which means f and h plus del f upon del t must be equal to 0. Even if it is not necessary, it is explicit function of time or not explicit function of time. Suppose f is not explicit function of time, then what you have to do? You have this f and h must commute. Then only this f will behave like a constant motion. Otherwise, this whole term must be equal to 0. There is a myth. There is a myth. Suppose I have some function and that function is explicit function of time. You cannot claim that this function is explicit function of time and it will be not constant of motion. This is very important. Only visualizing this thing del f upon del t is equal to 0 will not ensure you that that function will be constant of motion or not. What will ensure you? Ensure you that total derivative. The total derivative means f and h plus del f upon del t. But in case of Hamiltonian, But in case of Hamiltonian, you can see this is very interesting. If we want to write dH upon dt, if we want to write dH upon dt, then what we have? We have H and H plus del H upon del T. And this will always zero. H will always going to commute with Hamiltonian. So for the case of Hamiltonian only, you can write dH upon dt is equal to del H upon del T. And for the case of Hamiltonian, if H is explicit function or H is not explicit function, H is not explicit function of time, then only it is conserved. But for other physical quantity, this is not enough. Sorry. For other physical quantity, this whole term must be equal to 0. Do you understand or not? When we will do the problem, you will understand the proper thing. The real thing is F and H. What is the relationship between F and H? Then it will come to what will be del F upon del T if it is explicit function of time. So only if I will give you some expression and what I will say you that, okay, see this expression, can you say this is constant of not? You have to ask for which system. Suppose I am giving you system, then you have to write the Hamiltonian. And after writing the Hamiltonian of that particular system, you must check whether these all things are equal to 0 or not. If these all things are equal to 0, then only this F will be constant of motion. So only explicitly of time, the function which is only dependent on time, is not enough to determine which is constant or not. But yes, that is enough for case of Hamiltonian. That is enough for case of Hamiltonian, because for the Hamiltonian, the total derivative is equal to partial derivative with respect to time, actually, with respect to time. And this is a wonderful thing. You will mesmerize when we will solve 2 and 3 problem, that it will break your myth that what is happening here. So let's try to just go for the problem, and only the problem can give you better concept. Otherwise, what is meaning of this particular frame? Meaning of this frame that explicit function of time or not time will only meaningful for Hamiltonian. For other function, these two term is meaningful. For other function, these two term is going to meaningful. Whether it is conserved or not conserved, not only this term is decide, rather F and H will also decide. The commutation between F and H will also decide. So let's go for problem. We will start with the basic problem. But before that basic problem, we can write equation of motion in term of Poisson bracket also. So let's try to write equation of motion in term of Poisson bracket. So what you have, we have, let's say, suppose we want to write dx upon dt, or you can just write dqi upon dt, or dq upon dt, you can see anything. So dq upon dt is q h plus del q upon del t. And what is dq upon dt? Dq upon dt is equal to q dot. So this will equal to q dot is equal to q h plus del q upon del t. And what is q dot? This can be del h upon del p is equal to q h plus del q upon del t. So this is Hamiltonian equation of motion in term of Poisson bracket. And similarly, we can have dp upon dt is equal to p dot, and this can be also written as some p h plus del p upon del t. And what is this dp upon dt is minus del h upon del q is equal to p h plus del p upon del t. And now if you want to change this minus sign, I can change this one. So, and this one will also going to change, but I am just keeping this one same. So you can have this kind of situation that this is your basically Hamiltonian equation of motion in basically in Poisson bracket form. So you can have, this is one of a favorite question in your exam, that write down Hamiltonian equation of motion in terms of Poisson bracket. Okay, so this is quite simple. I am just going to discuss some trivial problem. You know the result, you know the particular result, and we will try to see what is happening here. And then we will go for some non-trivial problem where your myth is going to broken. So first we will go for trivial one. So what we have free particle. In one dimension free particle. What is my Hamiltonian? Hamiltonian for free particle is, let's say, px square upon 2m. This is Hamiltonian for free particle. Let's try to find whether px is constant or not. Just we have to check the linear momentum is constant or not. And we know for free particle, linear momentum is always constant, but we can check it here. What we have, dpx upon dt must be equal to, I can just use this thing. I am using this particular thing. df upon dt is equal to f and h plus del f upon del t. So we can just write dpx upon dt is equal to px, and this will be something px square upon 2m, and this is not an explicit function of time, but px and px square is going to commute. So this will be dpx upon dt is equal to 0, which implies px is constant. Which implies px is constant. Yes, we know this thing. We know this kind of situation that yes, px is constant. Let's go for the same thing for harmonic oscillator. For harmonic oscillator, what will be Hamiltonian? Let's say Hamiltonian is px square upon 2m plus half kx square. And again, we want to check whether px is constant or not. And we know for harmonic oscillator, then linear momentum is not conserved. So we just want to see whether linear momentum is conserved or not. So what we will do, again, we are using this thing. So we have dpx upon dt is equal to px h plus del px upon del t. This is not explicit function of time right now. This is dpx upon dt, and there will be px plus px square, sorry, px and px square by 2m plus half kx square plus 0. We have two commutation rule. So first is px square upon 2m, and here we have px and half kx square. So this value is 0, and if we are going to calculate this particular value, px and px half kx square, I can take half kx, half k common. We have px and x square. So what will be p and x square? If you will calculate it, you will get 2x is the value. How you can get it? You can get something. So I am just writing that I am just going to calculate this particular thing. So we can write pxx, the commutation of pxx, x plus, and just I am using this portion. We have px x and x plus, again I will write x pxx. I am writing x square as x into x. So this is pxx is minus x, sorry, minus 1. So this is minus x plus x, and this is also minus 1. So this will be minus 2x. So when we will going to put it, this value is nothing. Half k minus 2x. So this 2 is cancelled. Minus kx the thing. So what we have? We have for harmonic oscillator dpx upon dt is equal to minus kx. And what is this? This is nothing but force, and which is not equal to 0. Actually, it is not equal to 0. And if it is not equal to 0, dpx upon dt is equal to minus kx, not is equal to 0, means the px is not constant. You can just use this particular thing. So we can say px is not constant. So this is a particular thing we have seen in the harmonic oscillator. Why I am doing these two things? Here, P is also not explicit function of time. Here, P is also not explicit function of time. But you can see, here we have Px act as a constant of motion. But here, we don't have Px is not act as a constant of motion. Why it is not constant of motion? Because there is force into x direction. This px upon dpx upon dt is nothing but minus kx. This is force into x direction. So whenever force is in some particular direction, the linear momentum is not going to conserve. We have learned from our childhood. So that one particular myth, here we are talking about physics, that okay, this is my momentum, this is my something else. But sometime there may be some new type of function, and that function will maybe function of time, may not be function of time. How will you say that whether it is constant or not? Only just if it is function of time will not allow that it is not constant, or if it is not function of time, then you can say okay, this will be always conserved. This is not going to happen. It will all depends on what is the relationship between Hamiltonian and that particular thing. This is very trivial because we know what is the relationship between momentum and the Hamiltonian. We know that okay, there is force into x direction, so why momentum is not conserved. But if I will just go for any arbitrary kind of situation, then how you will judge? This is the actual challenge, and this challenge is solved by this particular equation. Now we will go for non-trivial one. Otherwise, if you want any question, you can just ask me. Now that guy who have asked me the first question, he should be very much focused what we are going to do. So let's go for a wonderful question, and we will just try to see what is going to happen. So I think everybody is okay. Okay. So let's go for this. Now, what is going to happen? This is a very interesting kind of situation. Look at here. Suppose we have free particle, and we know the Hamiltonian of free particle. The Hamiltonian of free particle is, let's say, px square upon 2m. And we have some particular f, some function. What is this f? F is equal to x minus px m upon t. Look at this, f is function of time. This f is function of time. What we want to know, we just want to know what will df upon dt for free particle. Yes, you can see that this is non-trivial problem. Why? Because there f is function of explicit function of time. You can have del f upon del t, and this will be minus px upon m. This will be minus px upon m. So this is explicit function of time, and which is not equal to 0 actually. So this is explicit function of time. Let's try to find what is going to happen, and we are discussing for a particular system. And what is that system? That system is identified as free particle. So this is something free particle. So this is free particle. I am just talking about free particle. What is going to happen here? So we have tool, and this is a wonderful tool. What we have, df upon dt is equal to f h plus del f upon del t. And what is f? F is nothing, x minus px t upon m, and this will be x. H is nothing, px square upon 2m plus del f upon del t. Now, the first term will be x px square upon 2m minus we have pxt upon m, px square upon 2m plus what is del f upon del t is nothing but minus px upon m. This term is 0, and we can just calculate this particular term. When you are going to calculate this particular term, we can just find this value is nothing. So x and px square by 2m. So I can take 1 upon 2m common. We have x px square minus px upon m. And now this will be 1 upon 2m. We have x px. I can take px. Again we have x px. I can take px minus px upon m. X px is 1 upon 2m. Here we have px. X px is 1. So 1 into px plus px into 1. And we have minus px upon m. And what is beautiful part? That beautiful part is 2px upon 2m minus px upon m. And this 2 and 2 is cancelled. What we have? Px upon m minus px upon m. And this will be equal to 0. What is going to happen? Even if it is explicit function of time, then this term df upon dt is equal to 0. So what I can say, f is constant for free particle. Even if this is function of time, even if this is function of time, for the free particle, this particular constant, this particular thing is a conserved quantity. You can have one more conservation law. Momentum is one conservation law, and you have whatever be the name of this conservation, this F. I don't know what is its physical quantity, but yes, mathematically I can treat this is one conserved law, even if it is explicit function of time. This is a wonderful thing. If you have any doubt, you can just ask me. Let's try to identify what is this particular conservation thing. What is this? What is physically, what is meaning of this particular thing? We will try to identify, but before that, you must appreciate this particular mathematics.
So, sir, f is any function acting on the system.
I don't know what is F. F is some physical quantity. You can name some physical quantity.
Defined on R particle.
Defined on free particle.
Okay.
Everything will be constant or not constant depends on what is your system. Means this quantity will conserve if my particle is free. I don't know what is this quantity. This is some mathematical quantity. That's it. I don't know what is actually this quantity, but I will figure it out. What is this quantity?
Sir, how the second term will become 0?
How this second term becomes 0? Whose term is going to 0?
The pxt.
Px and px will be commute to this each other. Then it is 0.
Time.
And time is always commute to. Where is time into the Poisson bracket?
So this px term.
Just you can differentiate it dpx. Okay. Only two variable is x and px. The time will treat it as a constant because you are taking the partial derivative, isn't it? Now let's try to figure it out. What will be this f? We cannot figure it out in every problem, but it is free particle, so we can figure it out. What is this particular f? Let's try to find what is this particular f. Look at. So I am leaving this thing here. Let's try to find Hamiltonian equation of motion. So if we have Hamiltonian, this is my x and this is px square upon 2m. Del h upon del x is equal to minus px dot. That will be equal to 0. Del h upon del x is 0. So px dot equal to 0. So what is px is equal to some constant. Let's say that constant. So this is, let's say px dot is 0 right now. Leave it. So px is some constant. So you can just write px is some constant. So there is not any problem. So we have seen that in problem px is constant. Now the second equation, del h upon del px is equal to x dot. And what is del h upon del px? That is px upon m is equal to x dot. And what will be dx upon dt is equal to px upon m. So this is constant. So I will treat this as a constant. So what will be x? X can be written as pxt upon m plus some constant, another constant c1. And now you can see this particular c1 is nothing. This particular c1 is nothing. X minus pxt upon m. And if you are going to compare these two things, this is nothing but the integration constant. This is nothing but the integration constant. And I have proved that this is constant for this particular thing. You can see this C1 is nothing but your F, and this will be X minus pxt upon m. Who told you that this is constant? Who told you? You have just arbitrarily defined that, okay, this is my constant of integration. But I have proved that no, this is also constant for this particular free particle. We have just df upon dt is nothing but 0. So why you can see. So this physical quantity is nothing but the integration constant depends on initial condition. What is this particular initial condition? And now you have this particular constant. So you can have this mathematical quantity, any mathematical quantity, you can prove whether it is constant or not constant. It is never, it will never work for whether it is time explicit function of time or not explicit function of time. Only this quantity will define df upon dt is equal to f and h plus del f upon del t. Only these two quantity will define whether they are constant of motion or not. So the myth is going to break. Yes, this is explicit function of time, but even if it is constant of motion, because its relationship with Hamiltonian is so beautiful that ultimately it is coming out of constant of motion. So let's go for one another non-trivial example. If you have any doubt, you can just ask me. Okay, so let's go for one more problem. So let's go for simple pendulum. For simple pendulum, I know my Lagrangian, let's say Lagrangian is half m L square theta dot square plus mgl cos theta. Suppose this is your Lagrangian. What I just want to know what will be dh upon dt. This is my first question. What will be dl upon dt? So two things, and please, this Lagrangian is not explicit function of time. This Lagrangian is not explicit function of time. So del L upon del T is equal to 0. So this is equal to 0, you know. Let's try to find out what will be dH upon dt. So first we have to go for writing the Hamiltonian. So Hamiltonian is all about P theta, theta dot minus L. And what is theta dot? Del L upon del theta dot is equal to P theta, and then this will ml square theta dot. So theta dot is equal to P theta upon ml square. We know this relationship. I have done it in last class also. So this is PL square, P theta upon ml square. I can put here, and what I will get? I will get Hamiltonian as P theta square upon 2ml square minus mgl cos theta. So this is my Hamiltonian, don't worry. I have done into last class, so I didn't do any calculation, but I can use it. Now let's try to find what will be dH upon dt. So obviously dH upon dt will equal to h and h plus del h upon del t. H and h is always going to commute. Del h upon del t is 0 here, so this is 0. I can say h is constant. I can say h is constant. Yes, and that constant is identified as total energy of a system. This is nothing but what? Total energy of a system. This is my constant, and this is identified as total energy of a system. Let's try to find what will be dl upon dt. And we know L is T minus V. We know L is T minus V. Let's try to calculate what will be total energy. So obviously we have dH upon dt is 0, which implies H is a constant, which is identified as energy. Let's go for dl upon dt. So first what we have to do, we have to just write L as a function of theta and p theta. Mathematically we can write it. So L can be written, so theta dot can be replaced p theta by ml square. So this will be half ml square. This will be p theta upon ml square whole square plus mgl cos theta. And this will be p theta square upon 2ml square plus mgl cos theta. Now what is dl upon dt? The dl upon dt is LH plus del L upon del T. Please, del L upon del T is 0 because it is explicit. It is not explicit function of time. Let's try to calculate what is del L upon, sorry, what is commutation between L and H. So you have del L upon del theta, del H upon del P theta minus del L upon del P theta, del H upon del theta plus 0. This term is 0. Let's try to calculate each and everything. So we have L as a function of p theta. We have L as a function of p theta. So I am writing it here. Then we can calculate it very nicely. What we have L as p theta square upon 2ml square plus mgl cos theta. So let's try to go for this. Del L upon del theta is minus mgl sin theta. Del H upon del P theta, we have H. H is, we have written P theta square upon 2ml square minus mgl cos theta. So this is the thing. Minus mgl sin theta. Del H upon del P theta is equal to P theta upon ml square. This is P theta upon ml square minus del L upon del P theta is equal to P theta upon ml square. Del H upon del theta is cos theta minus sin theta minus plus. So this will be sin theta, mgl sin theta basically. So this will be basically mgl sin theta. Now what we have, we can cancel all this term L and L. What we have minus 2g upon L p theta sin theta, which is not equal to 0. Which is not equal to 0. So what we have for the simple pendulum, the Hamiltonian is acting like conserved quantity, but Lagrangian dl upon dt is not equal to 0, means Lagrangian is not going to conserve. So only watching the Hamiltonian, you cannot say that your Lagrangian is also conserved. This is ridiculous. This is an entirely different kind of situation, isn't it? Look at this mathematics. Look at this mathematics. Only mathematics will reveal you at the higher level. When you have complicated system, you cannot say, okay, this is my, it is explicit, and both are not explicit function of time. Both are not explicit function of time. This is the one of the biggest thing. Even if both are not explicit function of time, you can see for the simple pendulum, the system is simple pendulum. I don't care what is mathematical form of Hamiltonian and Lagrangian. The Hamiltonian is conserved for the simple pendulum, but where Lagrangian is not conserved. And Hamiltonian and Lagrangian are related to each other. You can see, you can write Hamiltonian in terms of Lagrangian, you can write Lagrangian in terms of Hamiltonian. But even if one is conserved and one is not conserved. So it's a really wonderful thing that you can talk about conservation of any particular quantity. If you have any doubt, then you can ask me. And now the person who have raised that doubt, I think he's much more clear what I am going to say, what I wanted to say on my first frame. So let's go for one more problem. Then we will see. We will then obviously you can understand what is gist. The gist is all about you have to calculate the total derivative. This is your gist. Now let's go for one more calculation. This is also non-trivial one. So this is a, suppose Hamiltonian of harmonic oscillator is p square upon 2m plus half m omega square q square. So q is generalized coordinate and is generalized momentum. And let's say it's a very interesting function. Let's say this function is u and this function is something ln p plus I m omega q minus omega t. This is a, I don't know what is this particular thing. I don't know, but let's try to see what is happened to du upon dt for harmonic oscillator. This is for harmonic oscillator and this condition. So we have to check what is du upon dt. So what is du upon dt? So what is du upon dt? Du upon dt is easily, you will write u h plus del u upon del t. So be very careful to the calculation because it's not a very straightforward calculation. Log is there and all term is there. So what will happen? So du upon dt is equal to, we have log is 1 upon p plus im omega q. So I will just write first formula, then we can calculate it. So what will be this thing? Del u upon del q, del h upon del p minus del u upon del p, del upon del q plus del u upon del t. So just go for equation. So I am just doing this calculation here. So del u upon del q. Look at this is very important. So what you have, let us write it is small p. Okay, small p, because tomorrow we have bigger p. So we have 1 upon p plus I m omega q, and we have differentiating with respect to q. So this is I m omega is I m omega is, just go outside, then del h upon del p. This will be p upon m minus del u upon del p. Again we will go for this 1 upon p plus I m omega q. We will differentiate p, that is 1 is there, so there is not any problem. Del h upon del q. So del h upon del q, you have m omega square q, the half and half will cancel. Del u upon del t is minus omega. This is minus omega, isn't it? So we have this m and this m is cancel. So I can take I omega as common. So what will happen? P minus M omega by I Q minus omega by, and I is there. Sorry, this will be, sorry. There will be, I is also there. I is also there. Sorry, this will be, there is I. So there is I omega. Sorry, you can just go for I is also there. So this will be I omega by P plus M omega Q. And I can take I out above, then this will be plus. So what will happen? I omega P plus I M omega Q upon P plus I M omega Q minus I omega, this and this. So I omega minus I omega is equal to 0. So for the Hamiltonian, for this particular Hamiltonian, this quantity is conserved. U is constant during the motion. And look at how complicated is this particular U. This is P plus I M omega Q minus I omega T. Please correct it. This is I have left there. So look at this thing. So you have this kind of, this problem have come into last year into just examination. Then you have just find what will be du upon dt and this kind of situation. Okay. So I hope you, if you have any question, you can just ask me. Otherwise, you can take some assignment question also. So just go for assignment. So I think you should go for assignment 2 and let me check which question you can do. You can just go for question number 1 at least. At least you can go for question number 1. Question number 4 I have done. So just go for question number 1. Question number 4. You can go for question number 7. Just you can go for question number 7 and 12. 12 is also, yes, you can go for question number 1, 4, 7 and 12. 1, 4, 7 and 12. So just go for 1, 4, 7 and 12. Just try to first 1, then 4, then 7 and then 12. So these all things are depends on these type of calculation. So we will discuss all the thing tomorrow. So tomorrow is again we will go for next step for Hamiltonian. So tomorrow we will go for first canonical transformation, then generating function. Generating function will take 2 classes. So tomorrow we will again have different thing. If you have any doubt, you can just ask me. Or
सर
हाँ
सर डेल एल ओवर डेल पी इक्वल्स टू क्यू क्यू डॉट लिख सकते हैं
क्या बोले डेल एल अपॉन
डेल एल ओवर डेल पी इक्वल्स टू क्यू डॉट
नहीं ये क्यों लिखोगे एल इज फंक्शन ऑफ जनरलाइज कोऑर्डिनेट एंड जनरलाइज मोमेंटम ना
जनरलाइज्ड वेलोसिटी
ना जनरलाइज वेलोसिटी ना ठीक है
यस सर
डेल एच अपॉन डेल पी इज क्यू डॉट ठीक है
ओके सर थैंक यू
ठीक ओके मैथमेटिकली आप उसको चेंज कर लेते हो जरूरत पॉइजन ब्रैकेट की जरूरत के लिए ठीक है तो एक प्रॉब्लम हो गया ना यहां पर एल एक फंक्शन की तरह यूज हो रहा था ठीक है एल को हमने एक फंक्शन की तरह यूज किया ठीक है क्योंकि एल से ही जनरलाइज मोमेंटम को हम डिफाइन करते हैं ठीक है एनी मोर डाउट सो ओके So thank you. Take care.